All right, so before we get into today's lecture material, I want to bring something to your attention, and I can only hope that I have managed to not screw this up. So the math department has decided to do web work differently, or at least how you guys access web work significantly differently than they have done in prior quarters. So Brennan, the reason why you couldn't log into WebWork is because they broke it. And so the way to log into WebWork now is actually to go into a class that requires it on Canvas and then press the launcher thing. So I've added that here. And what should happen is if you click this link, it automatically logs you in. And then actually, when you click this thing, now it will automatically log you in. And then it should assign all of the homework sets to you. So I think this is a way for the math department to get around the fact that we've had so many issues with the purge and late adds and drops and all of that kind of stuff that it's a nightmare for them to constantly shuffle students in and out of various sections. So this kind of automatically handles it all for them. Hopefully it will be not too much of a pain in the ass, but we shall see. I've gone ahead and already gotten, I believe, the first 16 assignments all set up. So they're going to open in a staggered fashion. So homework 1 will open today because it's on the material that we're covering today. Homework 2 will open on Monday because it's on the material that we're covering Monday, and so on and so forth. I've set things up. I believe I talked about this a little bit on Wednesday. But the day after our next class meeting is the full credit due date. So effectively you have until next Tuesday, I believe, at midnight to receive full credit. And then if you have anything that you need to finish up, you have one more day and you'll get half credit on all of those things. And then after that point, the homework assignment is fully closed. If you need an extension or anything like that, please don't hesitate to ask. As long as it doesn't become a habit, I'm pretty lenient on it. So every now and then, if somebody just has something come up and they need a little extra time, please let me know. I got no beef with that, but you don't get an extension for every damn assignment. That's unreasonable. Okay. All right. So I believe I have explained how homework's going to work now, so we can talk about bigger and better things. Yes.
I'm looking at the web right now. If you go into it, it's open, but the due date is set for 2023.
Son of a bitch. So I'm the person that set all this stuff up. I will need to talk to Jason Terry about how this is going to work then, because I followed his damn directions and apparently it didn't mean shit. So this afternoon, I guess I will go back through and fix this. So chances are homework 1's due date is going to get pushed back until I can get this stuff sorted out so that you guys have an appropriate amount of time to work on things. All right. Can somebody shoot me a quick email to remind me to talk to Jason Terry about it? Do what? Let me, what happens when you throw it? You're not trying to access it through Canvas. You have to do it through Canvas. Okay, so that's not on it. Okay. All right, I'll get this sorted out. I hate new things so much. Okay. Gross. All right. So let's talk about basic electrical quantities. And to some extent, I will allow this lecture to be a choose your own adventure kind of thing. And by that, I mean, do you guys want to talk about voltage or current first? Voltage. Okay. So let's talk about voltage. So voltage is the thing that you're probably most familiar with. because we deal with it very, very regularly. Anytime we are changing the batteries or something like that, we are effectively applying a new voltage to a system. Okay? So I'm going to hit you guys with a mathematical definition. And I promise to God we are never actually going to use it. And the reason why I'm telling you that is because it's a little bit gross. It's a line integral that involves some electromagnetic field theory, which the overwhelming majority of you guys have never had, okay? So our mathematical definition for voltage is going to be V AB, and I'll explain what that means in a moment, is equal to the integral from B to A of E dotted into DL. So this E vector is an electric field vector. And electric fields occur whenever we have some amount of separation of charge. Okay. So this is a line integral. I think you guys are probably know what line integrals are at this point in your calculus series. Maybe. You might have heard it called the contour integral as well. But effectively, it's just an integral that's occurring over some fixed path. And our path is just from point B in a circuit, whatever that happens to be, we would define it to point A, some other point in the circuit, okay? Now, this is terrifying because it requires us to have an understanding of field theory, which I think is not particularly important for this level of class. So I'm going to introduce you guys with yet another field theory relationship that we can actually use to simplify this thing, okay? So another relationship, which you probably aren't currently aware of, but that'll be okay, is that electrostatic force F sub E is simply equal to Q times our electric field. So let me make a note here. So this is electrostatic force vector, and this is measured in newtons because it's a force, and for what it's worth, our electric field vector is typically expressed in volts per meter. Okay. So I can rearrange that first integral relationship for voltage because I can say that my electric field vector E is nothing more than F, my force, divided by Q. And since Q is the charge of an electron or the charge of a proton, it's a constant value, I can take that out of my integral, and what I'm going to wind up getting is 1 over Q times the integral from B to A of force dotted into some differential line element. So I know for sure that you guys have seen this relationship before. So what is the integral of force dotted into distance, or force times distance? Work, or energy, okay? So this bit right here is nothing more than energy. So from this mathematical relationship, we can say that voltage is the amount of work or energy required to move 1 coulomb of charge from point A to point B in a circuit. So this effectively tells us that voltage is what's known as an electromotive force, meaning we need a voltage present in our system to push electrons around and generate currents, okay? So if there isn't some voltage somewhere in our system, there cannot be current flowing in our system because it's voltage's job to push those electrons around and induce the flow of a current, okay? So that's one definition, and it's kind of telling us what voltage is doing. But we're going to have another definition that's going to be more applicable to this particular class and most lower level electrical engineering courses. And this is actually one that's talked about very briefly way back in Engineering 120 as well. And it has to do with the properties of a line integral, okay? So if we have a conservative force, and an electrostatic force is a conservative force, then a line integral is path independent, meaning it doesn't matter how you get from point B to point A or point A to point B, as long as those are your endpoints, any path you take will wind up giving you the exact same voltage. So we can think of voltage then. This is a second definition, and it's the one that we're going to use most of the time, as the difference in electrical potential energy between 2 points in a circuit. And the reason why I like this second definition so much is because it's fairly intuitive based on how we have been using multimeters and things like that to measure voltage in a circuit, right? So we've got one lead, typically the red lead would be our positive polarity terminal. We'll talk about that in a minute. And we connect it to one point in the circuit or one node in the circuit or something like that. We connect the black lead to some different point or different node in the circuit, and we are told a voltage. And what that multimeter is doing is literally measuring the difference in electric potential between those 2 points to tell us what that voltage is, okay? So the second definition is what we're going to use. We can always think of a voltage as just the difference in potential between 2 points, okay? So just like there's a difference in gravitational potential energy, if I move this stylus up some distance, there's a difference in electrical potential energy between any given 2 points in a circuit. And we're going to talk a little bit more about the rules as to how that goes, okay? So these are our definitions for voltage. Before we move on from this, are there any specific questions? Okay, so let's talk a little bit about how we are going to represent voltages, okay? So the first thing that I want to talk to you guys about is the concept of polarity, okay? So a voltage, so let's put this like so. A voltage is not fully defined unless we have both magnitude, so the strength of the voltage, and polarity. Okay. So let's say that I have some generic circuit element A. Like so. And this is another 2-terminal circuit element like we dealt with on Wednesday, okay? Let's say, just for the sake of argument, that generic circuit element A is representing a AA battery. So what's the voltage provided by a AA battery? It is not 3 volts. 1.5 volts, absolutely, okay? So I'm going to put 1.5 volts here, So that's my magnitude, but now I need to assign a polarity. So I'm just going to arbitrarily choose the topmost terminal to be the positive polarity terminal, designated by a plus sign, and the bottom terminal to be the negative polarity terminal, designated by a negative sign. If we pull up a quick image of a battery, Duracell AA battery. There we go. You might notice that one side of the battery literally has a plus sign on it, okay? And the other side of the battery may or may not actually have a minus sign written on it. But those are representative of the positive and negative polarity terminals of the battery. So batteries have a specific polarity. Things like resistors do not. So it doesn't particularly matter which is the positive polarity terminal and which is the negative polarity terminal. And we'll talk about what all that means here in a little bit, okay? So what these polarities effectively mean is that the positive polarity terminal has an electric potential that is 1.5 volts higher than the negative polarity terminal. So the negative polarity terminal is the lowest point of potential. The positive polarity terminal is the highest point of potential. Okay? So what if I chose for that same AA battery to just suggest that the positive polarity terminal was on bottom and the negative polarity terminal was on top? You could think about this as if we were measuring the voltage drop across a battery and we simply swap the leads of our multimeter around. What would that multimeter read? Negative 1.5 volts. Okay. So effectively, anytime that we wind up seeing a negative voltage, we can treat it like a positive voltage simply by swapping the polarities, okay? So we never have to actually give a shit about negative voltage or anything like that ever, if we just remember that we can swap the polarities around and turn that into a positive, okay? All right. So are we all okay with the concept of magnitudes and polarities? All right. So now let's talk about how we might represent voltages in circuits. And we've kind of already shown you one. So this format where we have a circuit element and then a positive polarity terminal and a negative polarity terminal, and then some magnitude, which I'm just going to call VS in this case. This is the American style of representing a voltage in a circuit. So for any given circuit element, we can assign a positive polarity terminal at one lead, assign a negative polarity terminal at another lead, and have some magnitude, and that is the American system. This is the one that we are going to use 99% of the time in this class, okay? Now, some of you may choose to watch better teachers than me from Europe or India or whatever, and their YouTube videos on circuit analysis. And the European style of representing a voltage looks rather different. So I just want to show that to you just in case you happen to utilize resources outside of the classroom, okay? So if we have some generic circuit element, like so, with some magnitude Vs, the European style is to draw an arrow where the tail of the arrow is at the negative polarity terminal and the head of the arrow is at the positive polarity terminal, okay? So if I drew an arrow down like this, we would have negative Vs, okay? So this is the European style. And I hate it. And the reason why I hate it is anytime I see an arrow on a schematic diagram, I immediately think of current, right? So it confuses me to have two different styles of arrow on any given diagram. And so I never, ever, ever use the European style in any of my lectures or anything like that, because if I find it confusing and I'm a jackass with a PhD, God only knows how difficult you guys will find it, okay? So you are now aware of it. You will never see it again in my class. Yeah. A third way to represent voltages, and this is one that I use in upper level electrical engineering classes very regularly, but not too often here in Circuits 1, is what's called the double subscript notation, okay? So in a double subscript notation, I need to give each node or each terminal a name. So I might call this 1 and this one 2. And I could write the magnitude of the voltage as V12. Okay, so this is a double subscript notation. Let me write that down. And for this particular thing, the first subscript is the positive polarity terminal. Second subscript is the negative polarity terminal. Okay. So V12 means the voltage at node 1 is higher than the voltage at node 2. V21 is just the exact opposite. So effectively, instead of flipping the polarities, we would just flip the order of the subscripts to get rid of a negative sign. Okay. We are going to use this, or effectively a modified version of this, when we talk about nodal analysis in a couple of weeks. So it's not something that we're going to see a whole heck of a lot in this class. And when we do see it again, I'll explain what's going on again, because we're not going to understand it unless we practice it, okay? But these are the different ways that you can traditionally represent a voltage on a circuit diagram or schematic diagram. Anybody have any comments, questions, or concerns about how we're going to represent voltages in this class? All right. So the last thing that we're going to talk about having to deal with voltages are then the different types of voltage sources. So there are 5 different types of voltage sources that we're going to see as we progress through this course. So I'm going to start with the one that you're all probably already familiar with, which is a battery. Okay. So this is the schematic diagram, or the symbol that we use to represent batteries in schematic diagrams. And technically speaking, this is the symbol for a single cell battery, like a AA battery or a 9-volt battery or something like that. Now, the battery pack that you guys effectively put together in your Engineering 120 series, where you had 6 AA batteries connected in series, that would be considered a multi-cell battery pack. And so the symbol for that effectively just adds another horizontal, or another couple of horizontal lines, okay? So if it's only 2, it's a single cell battery. If it's more than 2 of those lines, it's a multi-cell battery. Doesn't particularly matter, and a lot of people use them interchangeably, but technically there is a difference, and because I am a stickler for shit like that, I'm showing you what it is, okay? So this is a battery. And a battery is an example of a DC voltage source, right? So let's show you guys another one. So this is the one that I'm going to use overwhelmingly in this class. And this is a generic DC voltage source. So we've got our magnitude, Vs, And then there is a distinct positive polarity terminal and negative polarity terminal that is designated by the plus and minus signs, okay? So technically speaking, this is the type of symbol we would use for the DC power supplies and all of that kind of stuff that we have spread across this room that we'll use for our labs and all that kind of jazz. But it can also be used to represent batteries or literally any generic DC voltage source. So I prefer to use this symbol just because it's not specific and it works for any DC quantity. Okay. And then we won't see this guy until much later, a generic AC voltage source. So we've got a positive and negative polarity terminal associated with it, but there's also that squiggle in the middle that effectively tells us that the voltage is changing in time. So our magnitude isn't going to be a single number. It's actually going to be some sort of mathematical function that varies with time. That's all AC really means, is it's a time variant voltage source, okay? So instead of just having capital VS, where, by the way, I use capital letters to represent DC quantities and lowercase letters to represent AC quantities, I've got lowercase VS of T telling us, hey, this voltage varies as a function of time. Okay. So these three voltage sources are examples of independent. That's voltage sources. And what independent means in this context is that these voltage sources are going to supply whatever their magnitude tells us, regardless of what they are connected to. So it doesn't matter if I'm holding a generic DC source in the palm of my hand connected to literally nothing, or it's connected to a huge network full of resistors, capacitors, inductors, transistors, all that kind of jazz. If I say it's a 5-volt generic voltage source, it's providing 5 volts. Always, always, always. Can't be anything else, okay? So that's what independent means. It provides a fixed amount of voltage in this case, independent of what it is connected to. And now we're going to deal with our dependent voltage sources, which you guys are going to hate until you get used to them. So I'm going to have a diamond symbol or a rhombus, whatever. There's still a positive polarity terminal and a negative polarity terminal. And I'm going to go ahead and draw a second one of those over here on the right as well. These symbols are exactly the same, but they're going to represent two different things, and we're going to talk about that in a moment. So on the left-hand one, let's call this a voltage controlled. Voltage source, or abbreviated VCVS, okay? And on the right, we're going to have a current controlled. Voltage source. These are dependent sources. Because the value of the voltage that they supply is dependent on something else in the circuit, okay? And the way that we're going to tell the difference between the two types of dependent voltage sources is actually going to be from their magnitudes, okay? So a voltage-controlled voltage source is going to have a magnitude of K times some external voltage, where K is a scaling factor whose units are in volts per volts. And the reason why I'm making a point of telling you guys what the units for the scaling factor is because very often they will not be given to you, okay? So if you see a voltage-controlled voltage source, and you can tell it's a voltage-controlled voltage source because the controlling variable is a voltage, then you can intuitively know that the scaling factor K has to be in units of volts per volts or unitless, because think of it as the input is voltage and the output is voltage, so the scaling factor has to not have any dimension to it, okay? Our current controlled voltage source is going to have a scaling factor of R times IX, where this scaling factor of R has units of volts per amp. And this is our controlling variable, okay? So we can think of a current controlled voltage source like this. We have some current flowing in our circuit somewhere, IX. It sees the scaling factor having units of volts per amp. So volts per amp times the amps of our current just gives us volts at our output, okay? So a current controlled voltage source effectively converts current into voltage, okay, by some way, shape, or form. Now, these dependent sources are used a whole heck of a lot to model the behaviors of amplifiers and transistors and things like that in higher level electrical engineering courses. As far as we're concerned with here in Circuits 1, it's just a magic box that I'm going to make you guys understand loosely how the input and output relationship works. And that's it. So this isn't something that you can realistically just go buy off the shelf. You can't go on Amazon and be like, I need to buy a current controlled voltage source. That doesn't exist. This is just a way to model some relationships that occur in the field of electrical engineering. And the easiest way to model them is treating them as if they were a source. All right, so this is the last topic regarding voltage. Anybody got any questions, comments, or concerns before we move on to current? All right, so just to recap things, I have defined voltage in a couple of different ways. A mathematical definition we will never look at again. And then two word-based definitions, one of them telling us effectively that voltage is what's pushing electrons or charge carriers along to induce currents. The second one, and the one that we're more likely to use and exploit, is that voltage is just the potential difference between 2 points in a circuit. We've talked about the magnitude of voltages and polarities and how to get rid of negative signs by switching polarities. And I have also shown you the 5 different types of voltage sources that we will regularly see in this class. Okay, so now let's talk about current. And specifically, I'm going to go ahead and add charge here. So current is nothing more than the word that we use to describe effectively the flow of electrons in a circuit, okay? Mathematically, I could say that my current, I as a function of time, I of t, is equal to the derivative of some time varying charge, q of t, with respect to time. So I'm just going to make a couple of notes here really quickly. Oh, I feel like an idiot. I'm going to have to go back up in a second. So this is current measured in amperes, where an amp, 1 amp is equal to 1 coulomb per second. And then Q of T is charge measured in coulombs. And the reason why I'm going to have to go back is because I never technically told you what the units for voltage were, although we all know it's a volt. So let me pop back up here and add that in real quick. I apologize for that. Okay. So voltage measured in volts, where a volt is equal to 1 joule per coulomb. Sorry for forgetting to tell you the units. All right. So the unit is volts, and a volt is a joule per coulomb. So for what it's worth, that first definition where we're told that voltage is the work done per unit charge tells us what those units should be, right? Because work is in joules, charge is in coulombs. So anyway, sorry for forgetting that. It's what happens when I don't bring my notes, but I'm probably not going to bring notes anymore anyway. Okay, so this is our one relationship. So we can say then from this that current can be thought of as the time rate of change, because we have a derivative relationship of charge passing a given point in a circuit. Okay. So effectively, current is just the rate at which electrons move around a circuit. That's all current is. Okay. We can mathematically rearrange this expression that we have here and get a relationship for charge in terms of current. Okay. So that relationship is going to be Q of t is equal to the integral of I of t dt. But now I'm going to mess with things very slightly here. Okay. So I'm going to put a thing down here, T naught. I'm going to put some bounds on my integration. Okay. So this T naught just represents some point in time where the charge is a known quantity. So this is an initial condition on our system. So I'm going to add a term Q of T naught over here. So this is just telling me this is effectively just based on what I know was happening in the past. Okay. And I'm going to integrate to some later point in time T. Now, the problem with this from a mathematical standpoint is that T is one of the limits of my integration, and it is also the variable with which I am integrating with respect to. So I'm going to fix that by putting a T prime here and here, okay? So these T primes are just our way of representing time with a dummy variable so that I don't have the exact same variable in the limits of my integration as I do in my function, okay? It does not indicate taking a first derivative. I will never use a prime notation in this class to indicate first derivatives or double prime notation to indicate second derivatives or anything like that. I will always explicitly write out derivative with respect to time or derivative with respect to time squared so that there is no confusion. So this prime is just a dummy variable. The reason why I'm choosing to use this in your math class is you might have done something by replacing it with a Greek letter. Well, the Greek letter for T would be tau, and tau has a very specific meaning in electrical engineering that I don't want to screw up. So I'm using T prime, okay? So let's put this particular relationship into use because it can be a little bit awkward until we get used to it, okay? So let's say that I have some current as a function of time measured in amperes, and it's going to be plotted against time measured in seconds. And just for the sake of argument, let's say that our current waveform looks something like this. Where, let's say, this is going to represent 2 seconds, 5 seconds, 6 seconds, and so forth. And this maximum value of the current is, let's call it 5 amps. And what we want to find is Q of 4 seconds if Q at 0 was equal to 1 coulomb. So we're trying to find charge based on what the current is doing. And we have some known amount of charge at t is equal to 0. So that's our initial condition, right? So effectively what we're going to be doing is we're going to say that is a G, not a Q, goodness. Q of t is equal to the integral from 0 seconds, which is where our charge was a known quantity, to 4 seconds, which is the time that we're interested in, of I of t dt plus Q at 0 seconds, which we know is 1 coulomb. So we're just going to add this 1 coulomb on at the end. It is not inside our integral, okay? Now, we could, if we were so inclined, break our current waveform up into a piecewise mathematical function, right? So I of t to me looks like it's going to be, let's see, so it's going to have a slope of 5/2 amps per second times time for 0 less than t less than 2. It's a constant value of 5 amps for 2 less than t less than 5. And it's going to have a slope of -5. Sorry. Can't. T minus 5 plus 5 amps for 5 is less than t is less than 6, and 0 amps, excuse me, for t greater than 6. For what it's worth, what I'm doing on that interval from 5 is less than t is less than 6 is applying a time shifting, which you guys should have learned about in your pre-calculus classes. But effectively, I'm just using the y is equal to mx plus b format, and I'm just shifting that whole graph over to the right 5 time units. And my y-intercept at t is equal to 5 as this 5 amps right here, which is where this guy came from. So to be clear, we can do all of this weird math and then plug those things in. Or since we're taking the integral, what's our other option here? Find the area of this triangle and this rectangle, which I believe is probably the easier thing to do, okay? So we can throw a shitload of math at it if we want to, or we can think about things critically and just say that, hey, I'm just looking for this area plus this area, and that's going to give me the exact same result as integrating over those particular intervals, right? So what's the area of that triangle? So it's a right triangle, so what's the equation for the area of a right triangle? You guys are going to literally break my heart if you don't know it. 1/2 base times height, right? So 1/2, our base is 2 seconds. Our height is 5 amps. Then we have a rectangle. What's the area of a rectangle? Base times height, right? Length times width, same dealio there. So the base of this thing is 4 minus 2, so it's 2 seconds. The height is 5 amps once again. And then we have our 1 coulomb amount of initial charge in our system. So that's half of 10 is 5 plus 10, so 15. What's an amp times a second? A coulomb, right? So 15 coulombs plus 1 coulomb is 16 coulombs. Okay. So before we move on from this, I want to tell you guys about the amount of calculus I'm going to expect you to be able to do in this class, and the bar I feel is pretty damn low. Okay. So I am expecting you to be able to integrate and differentiate simple polynomials. So, x cubed plus 5x plus 9 kind of things, nothing too crazy there, right? You can take the integral or the derivative of that pretty easily, and if you can't, your calculator can. Some trig functions, specifically cosine and sine. Never really going to worry about tangent too much in this class or anything like that. So integral of cosine, integral of sine, and then exponential functions. So e to the x or e to the alpha x or something like that. That's pretty much it. So if you can integrate and differentiate simple polynomials, sine and cosine functions, and exponential functions, you have all of the calculus you will ever need in this class. Every other thing that I'm going to give you where you're quote unquote applying calculus is going to be graphs like this, where you're either taking the area of very simple shapes, right triangles and rectangles, or you're taking the slope of straight lines. Okay, so that's the level of calculus that you need to be successful here. So something asinine and simple like this, other than learning how to apply the equation, is absolutely fair game for tests. Okay? This is the level of difficulty I'm expecting of you. All right, so before we move on from this, does anybody have any questions about the relationships between current and charge? All right, so let's talk about how we're going to represent current, okay? So I want to start by saying that a current is not fully defined without a magnitude and a direction, okay? So going back to our simplistic generic circuit element A, if I say that there are 3 amps of current flowing through this element, that's all fine and dandy. But unless I also tell you the direction the current is flowing, I haven't provided you enough information to really do anything, okay? So let's say arbitrarily that there are 3 amps of current flowing down through this particular circuit element. If I were to ask you what the current flowing up through that circuit element was, what would it be? -3 amps. Okay. So if we have 3 amps flowing down, then we have to have -3 amps flowing up. So effectively, we can change the sign on the magnitude of a current by changing the direction the current is flowing, okay? So 3 amps left to right is the same as -3 amps right to left. 3 amps up is the same as -3 amps down, however you want to look at it. Effectively, we have a similar situation like we had in our voltage, but instead of swapping polarity to get rid of a negative sign, we simply swap direction, okay? So we always need both a current, excuse me, a magnitude and a direction to fully define a current, and we can change the sign of the magnitude by changing the direction of the current. All right, there's pretty much only the one way to represent a current in a circuit, and we've just shown it. It's using an arrow, okay? I can't think of any other ways that are commonly used, so let's just leave it at that. That is the generic all-purpose way of representing currents, is an arrow with some magnitude associated with it, okay? So now let's talk about current sources. My stylus is being dumb. Give me just a moment. There we go. All right, so current sources. So we are going to have 4 different current sources that we're going to look at or see and use in this class. We're going to have a generic DC current source. So the magnitude is represented by the value of the current source. In this case, I'm just calling it IS, but you'll probably see a number like 5 amps or 7 amps or something like that. And then the direction of current flow is in the same direction as the arrow, because that's what the arrow tells us, is what direction the current is flowing, right? So I believe this is fairly straightforward. One thing that I do want to point out to you all, so you're probably at least reasonably used to being able to go like buy batteries or something like that. So you can intuitively understand voltage sources or something that are, at least DC voltage sources, or something that readily exists and are available practically everywhere, right? You know, in a laboratory setting, you wouldn't use batteries. That would just be too expensive. So you would use DC power supplies and stuff like that. We have lots of those in this room, okay? Current sources are specialty pieces of electrical equipment. They cost thousands of dollars because it's effectively pretty damn difficult to actually design a circuit that supplies a fixed amount of current regardless of what it is connected to. It's a complicated piece of power electronics. I'm not saying it doesn't exist, but it is definitely not something Joe Schmo can go buy off the shelf anywhere, okay? So we're going to use these DC current sources a lot in when we're analyzing circuits and all of that kind of stuff, but out in the real world, unless you're an electrical engineer who's doing troubleshooting of electronics and stuff like that, you're probably not going to have a current source that you can inject current into systems with, because they're rather expensive, okay? All right, then we've got our generic AC current source. So exact same symbol, except that we put the little squiggle in it to tell us that the current is changing in time. And then I'm going to represent the magnitude of this as a lowercase is as a function of time. Once again, capital letters represent DC quantities, lowercase letters represent AC quantities, okay? So these are our 2 independent current sources. Once again, independent in this context means that they are simply going to supply that fixed amount of current regardless of what is connected to it. And then we have 2 dependent current sources. So we're going to have our diamond symbol, but now instead of having a plus and minus sign, we're going to have an arrow, which is telling us it's a current source. And once again, we are going to have a voltage controlled version and a current controlled version. So I'm going to call the current controlled version over here on the left. So this is going, and the voltage controlled current source will be over here on the right. And we're going to tell the difference between these two once again by looking at those scaling factors, okay? So for a current controlled current source, we're going to have K times some controlling current IX, where once again, K, our scaling coefficient in this case, has units of amps per amp or is a unitless quantity. Okay. And IX in this case is our controlling variable. And then for our voltage controlled current source, we're going to have lowercase g times Vx, where lowercase g has units of amps per volt. And then Vx is our controlling variable. Okay. And these guys are examples of dependent current sources. All right, so any questions about currents or anything? All right, so I've talked for a solid hour and change. I swear to God, we're almost done. Okay. So the last topic that I want to talk about is the relationship between power and energy. Okay, so those are the last two quantities that we are going to be interested in. So mathematically, power is simply the product of voltage and current. You guys should all be familiar with that. We can also think of it as the derivative of energy with respect to time, where power is measured in watts, and 1 watt is equal to 1 volt times 1 amp. Okay. Or 1 joule per 1 second. Okay. And then energy has units of joules. So we are going to define power to be the rate at which energy is absorbed / supplied in let's say to a circuit element. Okay. And we'll talk about that absorbed / supplied thing here in just a moment when we cover what's called the passive sign convention. Okay. Our energy relationship, W of t, is going to be simply the integral from some point in time we're interested in, which I'm going to call T1, to some later point in time we're interested in, which I'm going to call T2, of the power with respect to time. And so from this definition, we're going to say that energy is total amount of power absorbed or supplied by a circuit element over a fixed interval of time. All right. So this next thing that I'm going to talk about, and it's damn near the last thing, is the passive sign convention. And this is something that, for reasons that I can't figure out, and I've had 7 years of teaching this class to try to figure it out and still haven't figured it out. This seems to be, from a student perspective, one of the absolute hardest concepts to grasp. And I don't get it because I understand I'm a jackass with a PhD, but it's not that damn hard. Okay. So I'm going to try to explain this to you in the simplest way I can, because it's not, in my opinion, a particularly difficult concept. Okay. So passive sign convention, and this is related to power and energy. So let's say that I have a generic circuit element, A, like so, and I'm going to extend the terminals of this generic circuit element over to the left like this. Okay. And I'm using these ellipses right here to represent that this circuit element is connected to some larger circuit that is energized, so that we should expect to see some voltage drop across this element and some current flowing through the element because it's part of a circuit that's turned on. Okay. So I'm going to define the voltage drop across circuit element A as having positive polarity terminal on top and negative polarity terminal on bottom. And I'm going to define the current that's flowing in or flowing through circuit element A as flowing into the positive polarity terminal, and therefore it's flowing out of the negative polarity terminal. Okay. So in this particular configuration where current is flowing into the positive polarity terminal, the power absorbed by element A is simply equal to VA times IA, and the power supplied by element A is just negative VA times IA. Okay. So absorbed power is just the opposite of supplied power and vice versa. Okay. So anytime current's flowing into the positive polarity terminal, we have absorbed power. Okay. And that absorbed power is just VA times IA. So I did not say in any point in time here that the quantity VA is positive or negative, because it literally doesn't matter. Okay. Nor did I say that the current IA's magnitude is positive or negative, because it literally doesn't matter. If the current is flowing into the positive polarity terminal, VA times IA gives you absorbed power. Negative VA times IA gives you supply power. Okay, so that's our first case. Our second case, let's take some generic circuit element B. And now I'm going to define the voltage across B as positive polarity on bottom, negative polarity on top. And I'm going to have the current IB flowing into the negative polarity terminal or out of the positive polarity terminal. In this case, the power supplied by element B is VB times IB, and the power absorbed by element B is negative VB times IB. So effectively, current flows into the positive polarity terminal, V times I is absorbed power. Current flows into the negative polarity terminal, V times I is supplied power. That's all the passive sign convention is. So I hope you are all just as confused as I am as to why students don't seem to catch this, because it's pretty damn straightforward. If we're ever asked for absorbed power effectively for a given circuit element, and you're going to be asked that for your homework assignments, your in-class assignments and exams and all of that kind of good stuff, you simply need to look and say, all right, so did I define my current flowing into the positive polarity terminal? If so, it's just V times A, or excuse me, V times I. If I define my current as flowing into the negative polarity terminal, then it's negative V times I. That's it. Yes, sir.
Applied is always coming from negative to positive, and your absorbed is from positive.
Yep. Yeah. All right. The very last thing that I want to talk to you guys about, and this is also related to power and energy, is Telegen's theorem. Okay. So Telegen's theorem simply states that the total amount of power / energy absorbed in a system must equal the total amount of power / energy supplied in a, actually I should say circuit here and not system, but it doesn't really matter. It's the same thing to me. So effectively, this is just the law of conservation of energy for a circuit. However much energy we supply has to be equal to the total amount of energy absorbed. Otherwise, we are creating or destroying energy in our system, or creating or destroying power in our system, which is just related to the energy. That's Telegen's theorem. Okay. All right. Any questions on all of these basic quantities and relationships and all that jazz? All right. So you guys have, I think, around 30-ish minutes left to work on your in-class assignment. So please do that. If you have any questions about anything, I would be more than happy to answer them. Just let me know.